Learning outcomes. After studying this module, you shall be able to know about optical activity of enantiomers, learn how to resolve cationic and neutral enantiomers, identify the various methods for determination of absolute configuration of complexes, learn the X-ray diffraction method and spectroscopic method for determination of absolute configuration of complexes, analyze the different types of monochromatic polarized lights. Introduction. In this module, we will discuss about the optical activity of enantiomer. As we know that enantiomeric pair rotates the plane of polarized light in opposite direction. So, enantiomers can be differentiated only on the basis of their interaction with plane polarized light. In this module, we will also discuss about the resolution of various enantiomers, that are cationic enantiomers, anionic enantiomers and neutral enantiomers. We will also discuss about the determination of absolute configuration of coordination complexes. The various methods employed for the determination of absolute configuration of coordination complexes are X-ray diffraction method and spectroscopic methods. X-ray diffraction method is based on Bezoit analysis. However, spectroscopic methods are of two types. First is optical rotatory dispersion and second is circular diachorism. We will also discuss types of monochromatic light which will be used for the spectroscopic methods. The types of monochromatic polarized light can be plane polarized light, circularly polarized light and elliptically polarized light. Optical activity of enantiomers. The ability of chiral molecules to rotate plane polarized light is termed as optical activity of that compound. The plane of plane polarized light is rotated by enantiomeric pair in opposite directions. Enantiomers are usually differentiated from each other by their interaction with plane polarized light. Now, the question arises, what is plane polarized light? The plane polarized light is the light which oscillates in a single plane, while ordinary light oscillates in all possible directions. If a solution of one enantiomer is placed in the path of plane polarized light, the plane of polarization is rotated either to the clockwise direction or to the counterclockwise direction. The enantiomer which rotates the plane of polarization to the clockwise direction is known as dextrorotatory. It is labeled as dextro or d-isomer. However, its mirror image rotates the plane of polarization to the counterclockwise direction, which is known as levorotatory and is labeled as levo or L-isomer. The isomers of tris-ethylene diamine cobalt 3 complex are shown here, which is found experimentally to be the L-isomer of the ion. Its mirror image is d-isomer. Chiral molecules are called optically active due to their influence on plane polarized light. When a sample with a path length of L decimeter and concentration of 1 gram per milliliter is placed in the path of plane polarized light, the observed angle of optical rotation alpha is known as specific rotation of an enantiomer can be calculated by using equation, that is alpha T lambda is equals to alpha divided by L into C, where alpha is observed angle of rotation in degrees, L is the path length in decimeters, and C is the concentration of the enantiomer in gram per liter for a sample at temperature T and wavelength lambda in nanometer. When we use light with the wavelength 589 nanometers, which is the sodium D line, then the symbol D is also used. The sign of the rotation plus or minus is always given here. Now we can discuss the resolution of enantiomer. Resolution of cationic enantiomers. When an optically active compound is prepared in the laboratory, the chemical environment during the synthesis is not usually chiral. Consequently, two enantiomers are obtained in equal amounts, and this mixture of enantiomers is known as racemic mixture. The plane of polarization remains unaffected by a racemic mixture as the two enantiomers cancel the rotatory effect of each other. It is difficult to separate two enantiomers from the racemic mixture, but it is difficult to separate two enantiomers from the racemic mixture because the physical properties of enantiomers of a complex such as cis dichloro bis ethylene diamine cobalt 3 complex are identical except for their effect on plane polarized light. However, if the chloride ion, which is outside the coordination sphere, is replaced by optically active anions, the resulting salt might differ in properties such as solubility. If we want to separate the enantiomers from the racemic mixtures, the isomers must be treated with chiral compound. For example, the enantiomers of the previous complex can be separated into optically pure components by adding the chiral salt potassium antimonyl D-tartrate to an aqueous solution of the racemic mixture. The chiral tartrate form salt with both the left-handed and the right-handed isomers of cobalt complex. These salts are diastereomers because only one enantiomer of the anion is used. As diastereomers have different solubilities, the salt cis-D dichloro bis ethylene diamine cobalt D antimonyl D tartrate precipitates as yellow needles before the other diastereomer cis-L dichloro ethylene bis ethylene diamine cobalt 3 D antimonyl tartrate, one optical isomer. Separated diastereomers can be converted into D and L form by treating separately with concentrated HCl. The whole process of resolution of enantiomers is shown here. Antimonyl D tartrate can be replaced with D alpha bromo camphor pi sulfonate for resolving cationic complexes. Resolution of anionic enantiomers. Anionic complexes, for example, trioxylato cobalt 3 can be resolved by using optically active cations such as those formed by protonated strychnine or brucine bases. Resolution of neutral enantiomers. Neutral enantiomers cannot be resolved by the methods discussed above for cationic and anionic complexes because they cannot be converted into diastereomers. Thus, the physical properties of enantiomers towards asymmetric substrate may be employed to resolve optically active neutral complexes. As we know that the physical properties of enantiomers are different towards asymmetric substrate. These properties may be employed to resolve optically active neutral complexes. The methods are following: preferential solvent extraction from an asymmetric solvent. Second method can be preferential absorption on quartz and sugar from a solution. And third method is by using preferential gas chromatography or column chromatography. Now, we can determine the absolute configuration of coordination complexes. To establish the absolute configuration of a coordination complex and conformation of any chelate ring is of great interest for understanding the fundamental structure and bonding. Moreover, such knowledge is also used for the chemists who are dealing with stereospecific reactions. Therefore, determination of absolute configuration of coordination complexes is of immense interest. There are three methods for determining absolute configuration. These methods are X-ray diffraction method, spectroscopic method. X-ray diffraction method. In ordinary X-ray diffraction work, both the enantiomers give same diffraction pattern, thus gives no information about the absolute configuration of complexes. However, absolute configuration of complexes can be directly determined by the means of the anomalous dispersion of X-rays called Bijoit method or Bijoit analysis. In this method, the atoms in the structure provide a sort of 3D diffraction grating. To a first approximation, the diffraction effect is same whether diffraction is off the front or the back of the grating. This is called Friedel's law. But if the structure is asymmetric, then this law breaks down slightly, especially if the compound contains a heavier atom, example given a transition metal ion. This effect is known as Bijoit analysis. This is the only method of absolute structure determination which is not dependent on comparison between structures whose absolute configuration is known and the unknown one. If the structure contains an asymmetric fragment of known configuration, example given a chiral counter ion, no Bijoit analysis is necessary because the rest of the structure be consistent with the known fragment. The second method is spectroscopic methods. As we are aware that the lowest DD transitions in the hexaamine cobalt 3 complex is 1A1G to 1T1G, 1A1G to 1T1G. Thus, in case of complex prisethylene diamine cobalt 3 complex, a very similar electronic transition and visible spectrum will be observed. There are two phenomena associated with these DD transition, which are optical rotatory dispersion ORD and circular diachorism CD. These two methods are very useful in determining the absolute configuration of any complex. So, there are two spectroscopic methods for determination of absolute configuration. First method is optical rotatory dispersion and the second is circular diachorism, CD. Now, optical rotatory dispersion is defined as the rate of change of specific rotation with wavelength, whereas circular diachorism, which is the differential absorption of left and right circularly polarized light, is referred to as circular diachorism. Optically active compounds possess this special property of absorption of left-handed circularly polarized light to a different extent than the right-handed circularly polarized light. This difference in absorption of left-handed circularly polarized and right-handed circularly polarized light is known as circular diachorism. The behavior of optically active compound towards the polarized light is the basis of ORD and CD. The results can be interpreted by comparing the results with the compound having known absolute configuration. To understand optical rotatory dispersion and circular diachorism, first we need to know the difference between the normal light and the various polarized light. As we are aware that light is having wave properties. The wave is a sinusoidal oscillation of an electric and a magnetic field perpendicular to the direction of propagation of wave. The types of monochromatic polarized light. The unpolarized light usually consists of electric and magnetic fields oscillating to one another at right angles to the direction of propagation of the wave. So, for the unpolarized light, the electric and the magnetic vectors are observable equally in all directions perpendicular to the direction of propagation. For the polarized light, the oscillation is limited to the plane of polarization. Now, we can discuss the plane polarized light. When a polarizer is placed in the path of a beam of natural light, then the electrical or magnetic field of the developing light only fluctuates in a certain plane. This developing light is known as plane or linearly polarized light. Thus, in the case of polarized light, the fluctuation is confined to the plane of polarization, which is usually being taken as the plane of the electric field. Plane polarized light is already discussed in section 2 of this module. Now, we can discuss circularly polarized light. Circularly polarized light is the light vibrating along a circle lying in a plane perpendicular to the direction of propagation of light. A plane polarized beam of light can be mathematically described as two circularly polarized beam of equal amplitude spiraling in opposite directions. Therefore, two circularly polarized components of equal intensity combinedly create the plane polarized light. These two circularly polarized components are like left and right handed springs. If we observe the emerging wave, the right handed circularly polarized light rotates clockwise and left handed circularly polarized light rotates anti-clockwise. Two circularly polarized components can be resolved from the plane polarized light. The frequency of rotation of these components is related to the frequency of the light. Right-handed or clockwise circularly polarized light displayed with and without the component here. Right-handed or clockwise circularly polarized light would be considered as left-handed or counterclockwise circularly polarized if it will be viewed from the point of view of source instead of the receiver. Similarly, left-handed or counterclockwise circularly polarized light is shown here with and without the use of components. Left-handed circularly polarized light would be considered as right-handed or clockwise circularly polarized light if it is viewed from the point of view of the source instead of the receiver. Elliptically polarized light. When light vibrates along an ellipse lying in a plane at right angle to the direction of propagation of light is called elliptically polarized light. Generally, if the light oscillates in a particular plane in the space, then it is called linearly polarized. As the light is a diagonal electromagnetic wave and natural light is usually not polarized. So, all planes of propagations are equally probable for natural light. Two plane light waves with equal amplitude and differing in phase by 90 degree generate circularly polarized light. However, two plane light waves with different amplitude and differing in phase by more than or less than 90 degree produce elliptically polarized light. The difference between linearly, circularly and elliptically polarized light can be understood by looking here. Summary. In this module, we discussed about the optical activity of enantiomers. We also discussed the methods for resolving cationic, anionic and neutral enantiomers. We also discussed the various methods for determination of absolute configuration of complexes, that is X-ray diffraction method and spectroscopic method. In X-ray diffraction method, the absolute configuration of complexes can be directly determined by means of anomalous dispersion of the X-rays called Bijoyt analysis. However, we have also discussed spectroscopic methods, which are optical rotatory dispersion ORD and circular diachorism CD. We also discussed the different types of monochromatic polarized light, which are linearly polarized light, circularly polarized light. Circularly polarized light can be of two types, left-handed circularly polarized light and right-handed circularly polarized light. And we also discussed the third subpart, that is elliptically polarized light.